This video is about probability and statistics for experimental methods. This material is covered in Chapter 4 of Bigliola and Beasley textbook. It's intended to be an overview of primary topics to supplement reading, and it will also be a walkthrough of several probability and statistics problems for the current lab assignment. Stated here, a large population of variable X is characterized by its known mean value of 6.1, standard deviation of 1.0 units, whatever those units are, and a normal distribution. Determine the range of values containing 70% of the population of X. So we have known mean and standard deviation, known normal distribution. Find the range of values for 70% of the data. So how are we going to do that? The solution involves this idea of using the Z table and determining, backing out Z for the range based on this known probability. So the probability is 70%. So how do we use the Z table? Well, Z table is one-tailed or one-sided, and so we're looking for 70% on both sides, or two-tailed, two-sided. So we have to divide that probability by 2 to look for something on the table. We're going to be backing out the Z value for the range based on what's closest to the 70%. So half of 70% is 35%. And if we just look up on the Z table, we see that the closest value for a Z is 0.3508. And so that corresponds with a Z of 1.04. So with 1.04 known Z, also with the known mean and standard deviation, we can define what the limits, the range of the 70% band is using those values, and it's shown here. Okay, so my calculation came out with 5.06 to 7.14 is where 70% of the data lies with this application. Another example, at a fixed operating setting, the pressure in a line downstream of a reciprocating compressor is known and maintained at a mean value of 12 bars with a standard deviation of 1 bar based on its history. What is the probability that the line pressure will exceed 13 bars during any measurement? Known mean and standard deviation, what's the likelihood, is one way of saying it, or the probability of exceeding 13 bars during any measurement. Okay, so again, we're going to assume normal distribution, and we're going to use our Z value. So in this case, we have a known mean X prime of 12 and sigma of 1. And so 13, the value of X that we're interested in, minus 12 over 1 is a Z of 1. So we use our table 4.3, and we see when we look up a Z value of 1.0 that the probability is 0.3413. So we're not done there, because the question was about having a measurement outside or greater than 13. So the sum of probability on the right side of this graph is 50% or 0.5. So if we want to know what's greater than 13, we just take 0.5 and subtract off the probability at 13, and that's 0.5 minus 0.34, or 16% probability that there'll be a measurement outside of 13 bars. So that's that problem. So go ahead and take some notes on that one, visually shown here on the right. Next problem, probability of result due to random chance. A student conducts a lab exercise to calculate the acceleration of gravity G and gets a value of 9.5 with a standard deviation of 0.1. Now we know the true value of the gravity in this case is expected to be 9.8. So what's the probability of getting this result due to chance or random error alone? neglect outright blunders. He's careful, experimental, and comment on possible cause of this result. So how are we going to do this? Now we have similar concepts. We've got a mean of 9.5 based on our tests, and a sample standard deviation of 0.1, known true value of 9.8. So we can compute a z from that, 9.8 minus 9.5 over 0.1, and that's a z of 3. So the probability of z being between minus 3 and 3 is 2 times the probability of 3. And so we use our table again. Let's go back here. We can't see it on that one. So table here of 3 at 0.9865 down there. Okay, so 0.5 minus 0.9865 times 2 to count for both sides. And we see that the probability of getting a measurement of 9.5 is 0.27%. So very small probability of random error alone, likely some kind of systematic error in the student's measurement. Another similar problem. Now we go into a specific set of sample size, a specific set of samples. So we have 19 measurements of a pressure controller. The mean operating pressure is 4.97 kilopascals with a standard deviation of 0.0461 kilopascals. If more measurements are taken, estimate the expected range of pressure for 95% of the measurements. So this time we have known sample size, finite sample size, and so n is 19. So we're going to assume a student t distribution and use our mean and our standard deviation to figure that out. So mean is 4.97 and standard deviation 0.0461. So we can compute our degrees of freedom new as 19 minus 1 is 18, and assume 95% probability and get our result. So if we look at the student's t, this is table 4.4. Well, let's see, we have 19, 95%. So 19 is right here, 95%, 2.093. So I'm sorry, the measurement is number of measurements is 19. So the degrees of freedom is 18. So 18 right here, 18 and 95% probability is 2.101. And so we just use our sample standard deviation and our mean and calculate the range there. Oops, actually, let me go back here. I think that there's two different problems. Yeah, estimate the expected range for 95% of the measurements. And so, yeah, so if we got 2.101 is our t, and then we multiply that times our standard deviation 0.0461, and then our mean is plus or minus t times standard deviation. That gives us 4.97 plus or minus 0.097 with 95% probability. So that's our range, 4.97 plus or minus 0.097 kilopascals. Actually, and so this next problem I showed here was actually a slightly different problem, similar from those 19 measurements of a pressure controller. The mean operating pressure is 4.97 with standard deviation of 0.0461. So neglecting other sources of error, state the population true mean at 95% confidence. So similar idea. We have our standard deviation, but this time we're going to use our standard error, which is standard deviation divided by square root of n, and that's little s of x bar. And so our estimated that true population mean is our sample mean plus or minus t at 18.95% times standard error s x bar. And so let's see what the value is. So the estimate for the true mean is 4.97 plus or minus 0.022 kilopascals at 95% confidence. Okay, next problem is about grading scales, and again, using statistics to determine A, B, C, and D. So professor grades students on a normal curve for any grade X based on the course mean and standard deviation developed over years of testing. The following applies. Well, the question then is how many students will get A's, C's, and D's given that there are 100 students in the class. So A is defined as the mean plus 1.6 standard deviations. B is between 0.4 standard deviations and 1.6 standard deviations. C is between minus 0.4 and 0.4 standard deviations. And X is between minus 1.6 standard deviations and minus 0.4 standard deviations. And F is below that. So let's take a look at solution. Actually, I have not put that here. So we got plus 0.4 sigma minus 0.4 sigma, and then we have plus 1.6 standard deviations, and then minus 1.6 standard deviations. And so those that again are going to get, oops, this is on the wrong page. Fix this, sorry for a sec. .6 sigma plus 0.4 sigma minus sigma minus 1.6 sigma. So our A's are going to be up here. Our B's will be in here. And our C's will be between here. D's here. And our F's down here. So we can just compute the probabilities for ranges. So we can say compute P 6, P of 0.4, and then we can use our basic probability. So probability of A is 0.5 minus probability of 1.6, okay. Which, if we look that up for our case, we have we're going to use the Z table, 4.3, and probability of 1.6 is 0.4452. So this is 0.4452. and probability of 4 is 0.1544, 0.4 from our z table. And so then 0.5 minus 1 probability of 1.6 is 0.4452, and that gives us a probability of 0.0548. So if there's 100 students, then 100 times 0.05 is 5 to 6 students will have A's. Okay. And similarly, sorry, this is a little messy here. The question for C's, probability of C's. Well, that's the interval range between plus and minus 0.4. So it's really just 2 times the probability of 0.4 standard deviations. And so that's 2 times 0.1554. So that's 0.3108. So the number of students with C is equal to 100 times 0.3108. And then the question of the probability of D. Okay, so that's just looking at this guy right here. Okay, so it would basically be the difference in probability between 1.6 and 0.4. And so that's difference between 0.4452 and 0.544. So probability of D is probability of 1.6 minus probability of 0.4, which is going to result in the solution here in probably a 0.289 or about 29 with a D. 29 Ds. 29 Ds, 31 Cs, and then we had let's call it 6 students with an A. So messy slide, but that's the general idea for how to do a normal curve with these particular standard deviation bands for 100 students. Okay. So the next problem is about probability of a measured value. So production of a certain polymer fiber follows a normal distribution with a true mean diameter of 20 micrometers and a standard deviation of 30 micrometers. Compute the probability of a measured value greater than 80 microns. So what's the probability of something that's greater than 80? And compute the probability of measured value between 50 and 80. We have 2 different problem sets here. So we'll compute our Z from our mean and standard deviation. So for 80, we have 80 minus 20 over 30, that's 2.0. We'll look that up in the table, and we'll get from that a probability of being 0.5 minus 0.4772, or 0.0228, 2.3%, small chance. So let's go back. So a Z-score of 2.0. Let's find that back on the table. So 2.0, that's 0.47 right there. So 0.477. We subtract off 50%, so 0.5 minus that gives us a small chance of being greater than 80. What's then the probability of being between 50 and 80? And so our second Z that we're looking at is 50. So 50 minus 20 over 30 is 1.0. And we can go back and look up the Z for 1.0. And that's 0.3413. And so the probability of being between these two values 50 and 80 is just the difference in the probability. Probability of 80 minus probability of 50, 0.4772 minus 0.3413, or 13.6% probability of a value being between 50 and 80. Okay, here this. Let's all that. Next example, batch of rivets is tested for shear strength. A sample of 31 rivets shows a mean strength of 924.2 megapascals and a standard deviation of 18 megapascals. Estimate the mean shear strength for the batch at 95% probability. The mean shear strength at 95% probability. So we have a batch where n is 31. So nu, our degrees of freedom, is n minus 1, or 30. We're going to compute a student's t for that. And so student's t will be based on the difference between a value and the sample mean over the standard deviation. So we're looking for 95% and find the estimate of the shear strength. So first we use table 4.4, go back to student's t for nu of 30 and 95%. Let's find that. Nu of 30 and 95%. 2.042. Yeah, 2.042. And right here. So then to get our estimate of our mean, we're going to use our standard error. So that's the standard deviation divided by square root of n. And so that is shown here. Standard deviation 18 divided by square root of 31. And so then our mean is our sample mean, 924.2 plus or minus 2.042 times 18 divided by square root of 31, which is 6.6 megapascals. So with 95% confidence interval, with 95% confidence, the actual mean shear strength will be between 917.6 megapascals and 930.8 megapascals. So we're going to use Excel to do this next problem. Experimental measurements are taken from a physical system that can be modeled by y equals b times x to the m. The experimental data shown here, 1.02, 3.27, 1.99, 12.25, and then so on. Find the coefficients to fit the model using the method of least squares and calculate the standard error of the fit. So note first that this is not how it's not y equals mx plus b, but we could get it in that form by using a log transformation. So we're going to convert that to that nonlinear to linear first, and then we're going to use the lin-s function in Excel. So let's go ahead and take a look at that. Okay, so with this problem, before we jump into Excel, let's just take a look at this idea of we have y equals b times x to m, and how are we going to transform that to be linear? Well, we just take the log of both sides. So log of y equals the let's see here. Log of b plus m times log of x. And so we can use whatever base we want. I'm using base 10 here. And so then at the end of the day, this is our new y. This is our new, essentially, intercept. We'll call this capital Y equals capital B plus capital M times our new x, which is, let's just call it capital X. So y equals mx plus b, where the y is log of y, b is log of b, and m is log of x. So essentially, we can fit that data here. And I'll do that in the spreadsheet. So in the spreadsheet, what we're going to do is we have the values for y, 1.0 all the way to 4.99. I'm sorry, the values for x and for y. We'll take the log of the x's and the log of the y's, and then we'll use the slope and the intercept functions to find the slope called m and intercept b, where our new model is based on the log of y equal to log of b plus m log of x. And so we have to, the m is straightforward. The m is 1.99, which is just what we're looking for. The b we have to transform back to be the original b by raising 10 to the power of this intercept. And so then we get a little b that's 3.14. So our new model has y equals b times x to the power of m, where m is 1.99, or about 2, and b is 3.14. Now, we can also compute the actual model result, or the fit based on our model, and the residual, and the square of the residual, and then we can actually sum that up. We can also use the lin-est function, which in Excel results in a bunch of important statistics, and then we can also plot that data. So plotting just raw y and x, we can definitely see a little bit of an exponential power law here. But if we take a log of both sides, we can see that it's actually linear in log space. So let's jump to this. So the spreadsheet here, you can actually see log of each of these values, log of the y's, and then our function here, we're just using the slope function, where our e's, 5 to 9, are the y's, and then our x's are right here. Likewise, we then use the intercept function. And again, there's a lot of different ways to do regression in Excel, but this just gives us our intercept using the x's and y's. And then here, we take our uppercase b and we transform it to lowercase b with the by taking it to the power of 10 to the power of b to invert the log transformation. So that's the idea, and then here's our computed value, where we just applied our slope and our intercept, and then we compute our squared residual, and we can square root, sum that up, and divide, in this case, by the degrees of freedom. And we can also see some of our stats over here, where you use this lin-est function, it results in each of these numbers shown. The first one on the top left is the slope, 1.99, which is the same as here. Then the intercept, same as here. But we get these bonus statistics. The standard error for the slope is shown here, and that's in the textbook called SA1. And then the standard error for the offset SA0 is shown here. The R squared is a very linear 0.999. 1.0 is the perfect linear or perfect fit, not perfect linear, but perfect fit. And then the standard error of the fit, which we call SYX in the textbook, is one of the functions that, one of the statistics that's reported by Lynn Est. Also F statistic, degree of freedom, sum of squared and sum of squared residuals here. So then in order to plot the data, you can just take a grid of X and Y's and plot that out. And so there is, there's our plot in non-log transformation. And there's our plot in log. So that is our first regression problem that was really a nonlinear regression problem. So the next problem is a regression, an actual linear regression, where we have 4 samples. I'm trying to fit a line to it, but we want to estimate not only the standard error, but the error at each value of X. And so we're going to use the Sheff band and manually calculate that in Excel. So the result is shown here, where the top and bottom band is shown in the separate series here, and the linear model is this red line. So over to Excel for that. So we have 4 samples of Y and X, 1 to 12, 2 to 13, 3 to 18, 4 to 9. And I'm going to go ahead and calculate out the xi minus x bar for the Sheff band. So the formula is shown right here. The Sheff band has this term in brackets that includes variation in x. So x bar, let's see where I computed that. X bar is B18. Yeah, so right down here I have my X bar and some other statistics here. I've got my T statistic at 95% is 4.303 for in samples. X bar is 2.5, and sum of xi minus x is 5. Yeah, so that's not necessary at this point, but so let's see my results using the linest function. I get my slope and my intercept, my error and slope, error and intercept, my R squared, which is 0.91, and my standard error of my fit, SYX. That's an F statistic, degree of freedom, sum of residuals and sum of squared residuals, I think what those are. And so I need to build up the computation for my intervals here. So I have my xi minus x bar squared, which is this top piece here. And then I need to also sum that. That's, I guess, let's see, that's what this guy is. Yes, C is summing these values, so it's the denominator here. And then on this guy, I'm doing my plus or minus T. T is, let's go ahead and put this equation and show all the details of it. T is shown right here, 4.303 times this guy, which is my standard error, 1 point of the fit, 1.26, times 1 over n, which is 4, plus sum of residual squared, or residual squared minus sum of residual squared. And then our YC is just the fit, the resulting Y model based on our regression. So it's just basically slope times x plus intercept. So if we look at that specifically here, we have this value equals B9, which is the offset or y-intercept, plus A4, which is the x value times the slope. And so similarly, you see that here, it's my YC, and then my YC plus my Sheff band, and my YC minus my Sheff band. And that is, that's what I'm looking for this guy. So let me show the chart here. And as you can see, that Sheff band gives a little higher uncertainty or uncertainty interval at the extreme ends of the fit here. Okay, so we'll go back to these slides and go to the next problem. Next problem is about figuring out the number of measurements for a specific criteria. How many independent random measurements of a time-dependent acceleration signal obtained from a vibrating vehicle under fixed operating conditions would lead to a confidence interval about the mean of plus or minus 0.5 Gs if the standard deviation of the signal is expected to be 1 Gs. Okay. So we'll figure out our confidence interval here. And so this is actually going to require a little bit of iteration. So how many samples? First, we are going to use this parameter D, which is a confidence interval divided by 2, and that's equal to t statistic times standard deviation over square root of n. And n is approximately this squared, the number of measurements required based on the approach outlined in the text. And so how do we do that if we don't know the number? Well, we use a guess and check method because, of course, the t statistic depends on the number. So say we might guess at first, let's see, I think we guess 16 at first, and let's see. Well, let's actually first calculate the numbers out. I'll try it that way. Standard deviation was 1, and D is 0.5. So let's see, where do we get that from? Yeah, expected signal of 1 gram. If the standard deviation is 1 and confidence interval about the mean is plus or minus 0.5 G. So the confidence interval plus or minus 0.5 is really just 2 times 0.5 or 1. So D is 1 over 2.5, 95% probability. So D squared over SX squared equals a quarter, 0.25, which we can start iterating from. So 0.25, what's close to that? Well, we can kind of look around here for 95%. And so we'll start with 16, and we get 0.264. And then next time through, we get 0.247. That's 0.25. I think there might be something wrong here. And ends up being n of 18. Let me check my numbers here. Okay, I'm just turning the video back to record. I actually figured out that I had a small bug in my slide here, so I just fixed it. It's shown here, actually highlighted in yellow. So let me just go over this one more time. So we're trying to figure out how many measurements are required for a given accelerometer test, where we want to be within plus or minus 0.5 of the mean with 95% confidence, knowing the standard deviation of the signal is expected to be 1. So we use this rule of thumb here of n being approximately equal to students t times the standard deviation divided by d squared, where d is the confidence interval over 2, and so plus or minus 0.5 is 1, so d is 1 over 2 or 1/2. Okay. We can't get t without knowing the actual degrees of freedom and knowing the number of samples, so we have to use a guess and check method. So rearranging this formula down here, we can see that we need to get a d squared over standard deviation squared of 1/4. So that's really 0.5 over 1 squared is 1 over 4. And so we're looking for this to be about 0.25 at 95% probability. And so we're looking to find the ratio of the square of students t over the number of samples to be about 0.25. First iteration, we try 16. So over here on 16 samples, we tried 17, which is the degrees of freedom of 16. We get a t of 2.120, and that gives us about 2.64. So we say, okay, what about number of samples of 18, which is degrees of freedom of 17, and we see that we have 2.11 students t, and that gives us about a 0.247 for this ratio of d to the standard deviation, which is close enough for what we're looking for. So we can then conclude that if we have a sample size of 18, that should allow us to use that accelerometer with a confidence interval of plus or minus 0.5 a g when we have 1 g of standard deviation. Okay, that's that one. So we'll move on to the next problem. So this is a problem about chi-squared. A company produces a computer battery that it claims that will last for 8 hours on a single charge with a standard deviation of 20 minutes. A random sampling of 7 batteries are tested and found to have a standard deviation of 29 minutes. What is the chi-squared value in the predicted level of significance as represented by the test? So the time of 8 hours is our mean, okay, and the standard deviation is 20 minutes. So that's 20 over 60 hours. So for a number of samples of 7, get a standard deviation of 29. So the chi-squared statistic is the degrees of freedom times standard deviation squared divided by the sample standard deviation squared divided by the population standard deviation squared. And so in this case, nu is 7 minus 1 times 29, the sample standard deviation squared over 20, the actual standard deviation, and we get a chi-squared of 12.615. So we go and look up, I think, table 4.6, and we see that for nu degrees of freedom of 6, chi-squared at a significance level of 0.05 is 12.6, which is pretty close to the chi-squared for our scenario. So the significance level, or alpha, is 0.05 or 95%. So the conclusion is there's a 95% probability that if the tests were repeated, the standard deviation would be less than 29 minutes, and a 5% chance that the standard deviation is greater than 29 minutes. So that's our chi-squared problem. Last problem, outlier detection. So we have a cantilever beam loaded at its tip. Tip deflection is measured. So we hung some weights, we measured deflection, and after 10 repetitions, these are the results. 5.3, 5.73, 6.7, 5.26, 4.33, 5.45, and so on. Test for outliers using Chevanot's criteria and recompute as necessary the mean value and standard deviation and get the best estimate of the true value for the data set. Over what interval would 50% of the entire population of the TIP values fall? So there's a spreadsheet that we're going to use for this, and we'll get to that in a second. The schematic of this problem, cantilever beam, some kind of deflection here, and this is each of our samples. So the Chevanot's criteria is 1 minus 2 times the probability of our z has to be less than or equal to 1 over 2n, the number of samples, where z is the absolute value of x minus x bar over standard deviation. So we use table 4.3 for our z, okay, and then we can use a spreadsheet to compute these values. So our DL, or our position in centimeters, is shown here, and then and we'll call that x. So then we have a mean of those values, and that's x bar. So then we take x minus x bar and square that. This is shown here, and then we get a z for each of those values, 0.5, 0.19, 1.85. And then from table 4.3, we look up the z for each of those values, and they range 0.195 all the way down to 0.087. So then we use our criteria, which is 1 minus 2 times the probability of a particular z value. So 1 minus 2 times this is computed here, and then we're comparing that for, is it less than 1 over 2n? If it's less than, we're going to identify that as an outlier. So all these values are greater than 0.05 except for this one value for number 5 right here. You can see visually that it looks like it's lower than others. So by the Chevanot's criteria, we would consider that an outlier. Now we might take that another stage of outlier detection, or we might just stop there. We could remove that one and repeat the same process, a second stage, and we might see that this one right here is an outlier in the second stage. But we have to recompute all of our statistics in that case. So for two-stage, we see the first stage here, and we have our number of samples, and then our standard deviation mean, and our standard error. And then here we take that value out and repeat the same calculations as we did here. And in this case, we actually identify that the third data row is also possibly an outlier, and we could take that out and recompute all of our statistics again. Okay, the very last question is just a p-value interpolation question. So given a number of samples of 20 and a known t statistic of 2.096, what's the p-value for this particular experiment? So it starts with looking up the t-value table 4.4 for 19 degrees of freedom. 20 minus 1 is 19. And when you look up the t-table that we have, we only have 50%, 90%, 95%, and 99% probability values tabularized. So we have to figure out where what t corresponds to, or what probability corresponds to a t of 2.096, because 2.096 is somewhere between 6 values for 95, 99%. So we just use an interpolation function where interpolating just involves taking the difference between the known values, 99 minus 95 for the probability, and then 2.861 and 2.093 for the t, consider that equal to the value that we're trying to find, x minus 95 over t that we have, 2.096 minus 2.093. And so with that, we can compute a p-value of approximately 95, actually a probability of 95.01 based on solving for x here. And then a p-value is 1 minus 95.01, so it's 0.0497. So the p-value is an indication that the probability indicates the probability that the numerical difference between two test values, such as the critical statistic and the test statistic, is due only to chance. And so if you have a small value, less than some threshold, 0.05 is often used, that's an indicator that there might be some significance to that test, and maybe some significance to something other than a random causing the relationship that's observed. So a very small p-value, less than 0.05, indicates the effects other than random are influencing the variation in sampling, and that the result is then significant. So in hypothesis language, if the p-value is less alpha of 0.05, you reject the null hypothesis. Otherwise, you do not reject. And I think that is all of the probability problems that we're going to cover. So it's worthwhile to go ahead and read that textbook.